everyone. Thank you all for being here. May-Kate's actually featured on this slide. Maybe some other pictures of her, I don't remember. May-Kate was my undergrad at Oberlin, so we have a bit of an Oberlin to UVM pipeline. So I'm going to start with a land acknowledgement. My students this summer during the pandemic decided we needed land acknowledgements for all of the places that we've been working. So these are written by my students. In China in particular, it's very complicated to think about land ownership. And so you'll see I'll be talking about 2 areas with indigenous land. But even those, they're not necessarily the people who have occupied the land for really long periods of time. So it gets a little complicated. So a big picture, I'm thinking about what happens when we cut down trees, what happens when we plant or replant trees. You'll see part of the story in China is about planting trees where historically there haven't been trees in an effort to have forests, more forests. And then what happens when we transition to organic agriculture. I'm going to talk a little bit about Cuba, water quality, chemical weathering, and dissolving landscapes, featuring a lot of May-Kate's masters in that. And then in China, I have 2 case studies from 2 different minority areas in Southwest China, and then a little bit of a regional analysis, which came from Veronica Sosa Gonzalez's PhD. She was a Rubenstein PhD student like a decade ago or so. So Cuba, the big picture we were trying to ask was, what was the effects of transitioning to organic agriculture? I'm not sure we have a good handle on that question, but that was the motivation for the project. We actually came up with the idea when May-Kate was studying abroad in Cuba as an undergrad. And this was funded by NSF, also got some funding from Oberlin, and then we worked with people from Williams and UVM and Oberlin, a lot of Oberlin students working on this project. So basically, we're looking at 26 catchments, did August 2018 fieldwork. We went back to Cuba for a second field season in 2019, but because of the pandemic, we've never ended up analyzing the data. We have piles of data from 2019 that we never did anything with. So I'm going to be talking about 2018 data from central Cuba. These are the sample locations that we had with varying amounts of agriculture. There's this narrative in Cuba that after the fall of the USSR, Cuba had a wholesale transition to organic agriculture because they stopped having the chemical inputs available from the Soviet world. I think on the ground, it's a lot more complicated than that. You still see sugar plantations. And so the narrative from the West in books like The Erosion of Civilizations is Cuba had this wholesale transition. You switch to entirely to organic agriculture. It's all small scale farms. And we did see some of that, but there is still industrial sugar agriculture. So it's way more complicated than what we were told before we went. So the first paper that came out of our Cuba work, Paul's the first author on it, was in GSA Today in 2020. And we were looking at water quality and chemical weathering. And we found that the E. coli levels were high if you're thinking about them for drinking water. This is a map of the E. coli. We were just laughing. May-Kate drank one of the samples that was a water sample from Cuba by accident because we, sometimes you don't have your field supplies and we didn't have water bottles to sample in because they'd been held up in customs. And so we just had little bottles and we sampled in bottles and they were in the fridge looking just like the bottles we were drinking out of. So that E. coli was high, but actually very similar to agricultural runoff in the States. It's just that we were never allowed to test the drinking water, so we don't know if it was being treated. Cuba was very, very strict on what we could do. You said you were doing this thing, you can only collect these samples. You cannot change your sample location, you can't change the day or the time that you're going to collect the samples. You're going to this place at this time, and this is what you're doing. So we couldn't say, oh, the E. coli levels are high, what does the drinking water look like? We weren't allowed to answer that question. The fertilizer use was very, very low. So this is our average dissolved nitrogen for 25 Cuban rivers, and compared to dissolved nitrogen coming out of the Mississippi River. And then total fertilizer use published elsewhere suggests that Cuba has lower fertilizer use than other areas draining into the Caribbean. So even though there's high E. coli, it sort of looks better than average agricultural land, which was kind of surprising and interesting and does suggest that this organic agriculture is helping the water quality. We also looked at the influence on chemical weathering. So we found these samples, this is mapped as marine strata. There was arsenic and other dissolved ions that suggest that you have a lot of evaporites. And so we have very, very high chemical weathering rates in this area. And so this is now make Kate's master's, when you go look at the chemical load coming out of Cuba, you have really, really high chemical weathering rates. So we have these high chemical weathering rates. Your rock dissolution rates are high. It doesn't correlate with anything, like it doesn't correlate with elevation, doesn't correlate with slope, basin area, precipitation. It's just pretty high, particularly for these 4 samples, which is where we had the evaporate. So, and it's really, really flat. So there's some mountains like in here, some low mountains, but basically we're talking about like flat landscape, agricultural, and the whole thing just seems to be like dissolving away with these high chemical weathering rates and rock dissolution rates. And Cuba's up here, but up here like with the rest of the Caribbean. So the Caribbean rates are high. So something with the tropical environment plus the rocks that we have in this area. We also managed to extract quartz out of these things. So we got brilliant 10 erosion rates. The quartz, this is what Paul's lab does here, is that you're working with quartz and it's giving you a background rate of erosion over the top 2 meters. And we find, if you're, this is like weirdly backwards. Okay. So your brilliant ton erosion rate is here and your chemical weathering rate is here. And I've lost my axis, I'm sorry. Your chemical weathering rate is here. This is a 1-to-1 line. And so we'd expect that if everything's being lost in this top 2 meters, that they'd be really similar to each other, or the beryllium rate would be higher. If you have sort of most places you have physical weathering and physical loss, your chemical data is lower. And we have much higher chemical weathering rates than we have brilliant 10 erosion rates. Which is a little surprising. The beryllium 10 erosion rates are very low. They're comparable to what we found in Namibia, which is very arid. So we're like, what is going on? And so normally we're thinking about the beryllium 10 erosion rates as being, as people talk about this being like a total potential of everything being lost from the environment. But if your chemical weathering rates are higher, then it can't be everything. So we have this deeper material that's being lost from being dissolved. And so what we think is going on is that you're dissolving the landscape very, very deeply. And then you have quartz that's just like sloshing around and mixing around at the surface because it's so flat that it can't go anywhere. And this is framing the way we think about erosion in tropical areas, in particularly in tropical areas and places with a lot of rainfall, because there's no reason that your chemical weathering has to be limited to the top 2 meters, right? If you think of an area that you have very deep soils, you have rainfall that's percolating really deeply, there's no reason you can't be dissolving stuff at depth and then having it leave in water. And that's just not being picked up with beryllium 10. And so we're getting, in Cuba in particular, because it's so flat, we're getting these low physical loss rates from the beryllium 10 from the top 2 meters, but very, very high chemical loss rates that we think are coming from at depth from rainwater that's percolating down, dissolving the rocks and removing them. And so that is a very big shift in the way that the cosmogenic radionuclide community is thinking about erosion rates, because it's not just happening in the top 2 meters. And so it's changed the way we sample as well. So we now are always collecting water samples when we go out and collect samples for beryllium 10, because the water samples will tell us what the chemical loss rates are as well. And that's where the collaboration from Williams has come in. And this was AK's master's. And we found that precipitation and slope have statistically significant correlations with loss. So some combination of the slope and the precipitation is driving the beryllium 10 erosion rate. But then when we combine them, I don't have this in the next slide. So when you combine them, you can get kind of a maximum. So if everything is being lost at depth, then, or everything's being lost on the surface, you can sum them together. So you have some limits. So like the higher of the two is the minimum amount you're losing, because it could be entirely chemical loss, some of which is in the surface, or it could be entirely in the surface if that's the higher one. And then the maximum is the sum of the two. So we can get some bound, but we can't get like a precise answer. We can say this watershed is eroding at this rate, which ends up being important from, like, if I think about applying this to environmental sustainability, if we want to know about ecosystem services and how much soil we're losing and what the environmental impact is, we want to have a better handle on how much material is being lost and where it's going. So we can learn about erosion in Cuba. The water quality is decent, but you shouldn't drink the tap water. Paul also had a story about drinking a bunch of tap water from Cuba. And And again, we just don't know. Like I've worked in China for a long time and people like to say Chinese water quality is terrible. The drinking water is terrible. If you go and test the drinking water, it's actually treated in most parts of China. We just think that it's not. And so we treat it all like it's not treated. We have no idea for Cuba. So you should drink bottled water if you go to Cuba. And the landscape seems to be dissolving deeply, but the beryllium 10 is not capturing the whole story. Okay, so China. I'm going to switch gears and talk about China. My family used to make fun of me that I only worked in communist countries that started with C. So I worked in China for a long time. I grew up in Hong Kong and I speak Mandarin. And so when I applied to grad school, it was like, I speak Mandarin. I want to work in Tibet. You should let me in because I speak Mandarin. And so I ended up working in China for a very, very long time and then transitioned to working in the Caribbean more recently. So this is some older work and some papers that have just come out. As a big picture, most of my work in China has been thinking about deforestation. So what does human land use look like in southwestern China? What are people doing to the environment? And what are the effects on erosion? And I've had like so many Oberlin students work on this project, I can't even count them all. Like at least 30 Oberlin students have worked on various aspects of work in China and have been in the field with me on a bunch of these different projects. So regional history, I think this is really, really interesting communist history. So we have like 4,000 years of human activity. A lot of it was non-agricultural and dispersed, but one of the areas I'm going to show you is an archaeologist I work with found that this was the oldest instance of wheat and barley agriculture in Western China. And the first places that transitioned from rice and millet agriculture to wheat and barley agriculture. So really, really interesting from a long-term indigenous land use point of view. In the 1950s to the 1980s, because of the Communist Party, there are these policies encouraging deforestation and expansion of agriculture. So cut down all the trees, so the Great Leap Forward, and then the Great Leap Forward, where they were encouraged to like cut down trees to make backyard steel furnaces everywhere. And then there's grain as a key link, which came after the Cultural Revolution. And the idea was put grain on every available surface, try to make China independent from the West be able to feed itself. And then in the 1980s with privatization and development, there was sort of back and forth, who owns the land and who can cut land for timber, who can harvest timber. And because it went back and forth so much, people were just like wholesale harvesting everything they could when they were allowed to. And so in the 90s, there was massive flooding on the Middle Yangtze River. And the government said, oh, that's because of the backwards people in the rural areas in the mountains cutting down too many trees, plant trees everywhere. And so there was a policy called Grain as the Key Link that was trying to reforest China, regardless of whether it was forested to begin with. So initially, the Grain as a Key Link policy, the Grain for Green, it's usually called Grain for Green. It's Gaige Kaifang, which is returning farmland to forest. You originally could return farmland to pasture or to grasslands, or you could return farmland to forest. But returning farmland to forest is like a better story internationally. And so they're planting forests everywhere, regardless of whether there have been forests on these surfaces in any meaningful way recently. So we're working in like mostly like Sichuan, like over here in Sichuan, but some big picture stuff in this sort of central area. Okay, so I'm going to do these two little case studies first, and if we don't have time for the regional stuff, that's fine. We'll just stop at the case studies. So Abilada was community-based research. This is a Nuasu area. They're classified as Yi by the Chinese, but they don't consider themselves Yi. They just say that Yi is the Chinese word for Nuasu. An anthropologist that I worked with for a long time was involved in building an elementary school in this village. And so we went back to the village regularly, and in his environmental anthropology work, people were like, our river's crazy. Like, what happened to our river? Why is our river undercutting houses? And so he was like, well, I know a geomorphologist. And so he went and got me and took me to this site. And I grabbed a University of Washington, now retired geomorphologist named Brian Collins. And we were the geomorph team in this site. We did field surveys, landform mapping, soil profile truncation and mapping, some geochronology, and then we worked with this anthropologist who did ethnography. This is some of the landforms. So we're mapping alluvial fans, terraces, and floodplains, and then dating a lot of stuff. So if we actually go back up here, so we don't have to look at the data for a second. Steve Harrell's interviews found that the Nwasu people moved into this area about 150 years ago. They have memorized their genealogy, sort of traditionally, they memorize their genealogy, and so they can go back X number of generations lived in this valley. They practice swidden agriculture on a very short cycle, about a decade cycle, on ridges and south-facing slopes, mostly on ridges. And then they pasture, so they grow crops for 3 seasons, and then they pasture animals for like 7 seasons, and then they plant again. So this is really, really short from a Sweden perspective. Before that time, the Permi people were living in the area, and they were mostly cultivating valley bottoms. But the Permi people were sort of pushed out as the Nwasu moved into this area. They would love the story to be that the problem was the Han Chinese coming in 1949. And that's the narrative that they really want, because the Nwasu are really maligned by the Chinese is very backwards. We found that most of the terraces, so this is deposition in terraces. This is absolute depth and this is fractional depth, but you can see that most of the depth is this this is the median and this is the mean. It's all in this window of exactly when the Nwasu moved to this area. So they move into the area, they start cutting down trees on hill slopes to practice this swidden agriculture, and this landscape just falls apart. And we map soils. This is near the village. We're measuring in centimeters. The forestry team that we went out with the first time was like measuring soil depths in like millimeters. And they went back and the soil scientists were like, why were you measuring in millimeters? Because like there's no soil, so basically no soil. And if we go 5 kilometers up from the village, we've got more than a meter of soil. And if we look at the depth of the A and B horizons with distance from the village, and this is just like a straight line distance, this isn't even like hiking distance, this is literally just like a Euclidean distance from the village. You've got a very strong correlation with soil thickness and distance from the village, suggesting that it is something about the long-term land use. And the people will say, oh, we were like scattered all over the hill slopes. But we know from the ethnographic work that starting around 1900, they were concentrating in the lower valley closer to the village. And so between the timing of the deposition and the thickness of the soils is not correlated with the tree age. So like tree age versus distance from the village is not related. The trees were all cut down under communist policies, but the trees are much bigger as you go farther away, suggesting more soils that are allowing the trees to grow larger. And that's going up in elevation. So this is not a climate effect, because the climate would have made the trees smaller. And so this is clearly related to the long-term land use in this area, which was really hard for the anthropologist, Steve, to wrap his mind around. We do think there was a sort of gallery forest on the bottom of the river that was cut down in communist times, and that is what made the river unravel. So like you have all these sediments in the bottom of the river, and they're being held together by the trees, and you cut down the trees and the river just falls apart. So I'm gonna show some pictures of the river. The local people are like, okay, what do we do? And we said, well, you kind of need to plant trees. So they planted trees, and the grandpas, the Aphus, put fences around them, and they also put some corn in, and they were like patrolling the fences to keep the pigs out and the goats out. This is 2009 up there. In 2010, you can see some of the trees starting, and they started planting corn. This is 2015. We happened to be there for like the 60-year flood in August 2015. Again, this is the 2009 photo. This is before the flood. This is the same area. Corn doesn't stop a flood. The corn ended up in the river, but the poplar trees do. So the trees that they had planted, that they had gotten to mature because they kept the pigs out, actually stopped the flood. So this is an ethical question I like to ask my students. We do a little case study on this in class. You've got this village. It has no people my age. So like the age of anyone in this room, they're not living in the village. They've all gone out to work. You've got grandparents and little kids. And the elementary school has now closed. That was externally funded because people care about education so much. They're taking the kids to the cities. They're often living in boarding schools from like kindergarten. But they're all going to college, which is awesome, at least for a Chinese equivalent of an associate's. You've got people in mud-walled houses cooking over open fires for their grandchildren. We've told them, you got to plant trees. They've built these like little Lincoln log structure things too. we don't feel right going in and being like, don't pull the wood out of the river. Like, what do you say to someone? The wood's down the river. We think wood is good for rivers. And they've sacrificed all of this time and energy to put these poplar trees in, and now there's this downed wood in the river, and they're going to take it out of the river to take it home to cook dinner for their grandchildren. We don't say anything. So even though from an environmental perspective, leaving the wood in the river would be better, largely this area is recovering in part because people aren't farming, because people are leaving to work in factories. But they asked us what to do, and we told them you've got to plant trees, and they planted trees, and they built these things. We were calling them Lincoln logs. Like, they built these little structures that they were putting in, and those didn't work so well. Really what worked was the poplars, and keeping the pigs out of the poplars. So a lot of this work has just come out in a paper in QR. There's like a more ethnography related paper that came out like in 2022, and with some forestry and ethnography, and then a more geo paper came out last year. So Jiuzhaigou is the other place I've done a bunch of work in a like particular location. It's a national park in a Tibetan area of Northwest Sichuan. It is an area that was not historically, it's a frontier area. So it's on the margins of like Tibetan and Chinese rule historically. People said that they turned to Lhasa for spiritual guidance, but they were usually controlled by Beijing politically. So they're like right on the border. The people are not Buddhist, they're Bon, which is the pre-Buddhism religion in Tibet. So I got really interested in these terraces here. I had written a paper that was published, and then I was giving a talk about this, and another geomorphologist said later, why didn't you mention that your terraces were on a landslide? And I was like, I'd never noticed that. So my terrace is on a landslide. This site here is where we found the evidence of the oldest wheat and barley agriculture in Western China. And we have this Paleosol Loess sequence, but often the stuff on top is gravelly. Like, how do we have gravel in the Loess? Like, what happened? Also, you can notice this is an older photo, but it's like clear, right? This used to be farming. And the local people will say they like growing on the Loess, the yellow soils, because it's better soil. So one thing I did was that you can notice, because of these reforestation policies, like 1999 compared to 2011, how much shrubbery has come in trees. And this is the like distribution of elevations. There's a kind of high flat plateau, which is why there's so much elevation so much land at higher elevations. And then this line is how much treeless areas, like went and mapped all the trees on satellite images. And you can see that the treeless area is being lost at these mid elevations. These are mostly south-facing slopes, and it's these kinds of elevations where people farmed traditionally, and they've been told they have to reforest them. But Tibetans have been living in this area for like 4,000 years, and you're now reforesting land that has been bare for like 4,000 years, particularly on south-facing slopes. There was actually a debate at one point on whether the slopes were naturally bare. And this guy, Daniel Winkler, who took this photo, was like, well, trees can grow, so it must be cleared. And I think that because there's a very strong gradient in plants that can grow at different elevations, you're losing biodiversity by planting, particularly they're mostly planting a monoculture, because you're reforesting all this land that has traditionally been cleared. There's a very strong elevation gradient in what can grow. We're losing biodiversity by going in and putting our monoculture in. Also, they control all fires and stop all fires immediately, so they're potentially really increasing big fire risk. We also were like, why are there rocks in the gravel in the Loess? Like, where'd the gravel come from? That's really weird. Actually, this is really cool as a side note. This is an exchange between the Makah tribe and the Tibetans in Jiuzhaigou. So two Jiuzhaigou employees, this woman, Kimo, is Tibetan, came and spent 3 months in Seattle, and then we took some Makah women to China to talk with them about indigenous land use and management, which was really fun. So like a ton of radiocarbon dates, some OSL dates, some sherds. So down here, these are like pot sherds that were dated from the archaeological site. And there's this linear age trend with depth suggesting that it's not just like one landslide that's been churned over. And then we have this older Loess, but we couldn't get very deep on the older Loess. It's just not exposed very much. So we're like taking advantage of these natural exposures. And this is much older. So this gap, for the climate people, this is like the mid-Holocene climatic optimum warming period in China, and this matches with regional trends seen in paleo lakes, like paleo lake research in cores. And then we have this modern, like nice sequence of modern Loess deposition. So where's the gravel coming from? the whole thing's a landslide. So this is my, I'm not great at conceptual models, sorry guys, this is like not the greatest sketch. It's my conceptual model sketch. We have a hill slope, we get loess on the hill slope. Soil forms on top of it during the mid-Holocene climatic optimum. People move in. So we know that the people start moving in above the Paleosol, like around the time of the Paleosol. And we start seeing the human evidence. This is partly from pollen and seeds and partly from like sherds and like stone walls and stuff that we're finding. And we know that there's the Paleosol, all these different levels, the loess, and there's gravel stirred into it. So we think the whole thing starts slumping. There's this really weak, shaly bedrock underneath, and the whole thing is just like falling apart. And then people are then spreading out the material that's falling off the terraces and mixing it into their terraces to farm. And you start having more loess come as the climate's cooling after 5,000 years ago. And as the loess is depositing, there's more landsliding, people are turning, like pulling this out and spreading it into their fields. And so you're getting this gravel mixed in, but the loess is coming. And so we think the deposition rates of loess are a little bit inflated because you've got people spreading out all the slumping material and you have the rocks being mixed in. But this is sort of a conceptual model for how we get this weird loess gravel, loess soil, gravelly loess sequence. We do think it's all the same. This upper loess is original loess deposition because we have some areas that have no gravel in the loess that's up high. Although that is a very, very tall cliff and we couldn't really get good samples on it because we just couldn't get up there to get the samples. And we think it's really interesting from a human perspective because people are able to live in this area because of the landslides. So if you don't have the landslides, you have stuff that's too steep for people to live. And once you start having the slumping, you have this flat surface, you have loess, which is great soil, and now you have a place people can live. So this is one of the many examples around the world where the hazards of living in this mountainous area also are what makes the mountainous area inhabitable. I'm gonna skip some again. All right, let's skip that. Okay. So in the end, when we think back, we've got Apilada, we have these modern changes that are overprinting long-term environmental change from human habitation. In Jodzai Go, we've got geologic hazards and human habitation that are like closely related. Modern reforestation policies, again, are probably unnecessary because people aren't farming, but also they're definitely inappropriate. We spent a lot of time in our group arguing that Chinese reforestation policies are inappropriate and even more than that, inappropriately applied. And periodically one of us who's an author on one of these papers will get an email or message on ResearchGate that's like, you shouldn't be saying this, this is against the Chinese policies. And we're like, well, they aren't really working that well. And they're, you know, planting this monoculture all over Western China. And so in Cuba, the organic agriculture seems to be making the rivers cleaner. Central Cuba seems to be dissolving. We'd like to do that analysis for Western Cuba. We haven't looked yet. And then in China, we're really thinking about like, how do you distinguish long-term indigenous land use from modern policies? And how do you untangle those in an area that has had people living there for such a long period of time?